Hello grade 12s, welcome to my channel, and hopefully you guys are doing great. If you're still writing your paper, your maths paper for the term 1 exams, this might help to get you into the groove. Otherwise, this video is essentially for those of you guys in the group who were not able to attend last night. So this is for you guys to catch up. So please make sure you watch and you practice. Do not watch and then sleep. Watch and practice. It's easy to see someone do the work and think you've understood it. When it stares you in the face tomorrow in the exam, you'll be like, what on earth am I going to do? So please guys, every skill you see someone display, reciprocate it, practice it, learn it, put it into use and explore it so that you understand how to use it and when does it apply, when does it not apply. Can you play tricks around it of your own so that you get comfortable with the subject matter, okay? So please guys, do not take these things for granted. A lot of students lose a lot of money attending these classes, a lot of money buying books, a lot of money getting into all sorts of things, and then after that they don't do their part and then they fail. Okay, so please don't allow yourselves to fail, guys. These are free lessons, and don't look at the fact that they are free and take them for granted. You will regret it, I swear to God. Anyway, let's just get to the work now, folks. We're talking about trig equations, okay? So now equations, literally we can think of them as functions, because these two terms are interchangeable, isn't it? An equation is some sort of a function if we think of it. So this helps us now to move ourselves closer to dealing with trigonometric functions on the Cartesian plane. But we're going to start with the algebraic aspects of them so that we can then apply the knowledge when we get to those functions. All right, so now there are some points to ponder, guys. Sine of any angle theta when it is equal to some constant p. Remember, p here is a constant. Meaning it has only one value. It doesn't change around. As much as I put it as a variable, it's essentially a constant. And this constant is placed between 1 and -1. So that is the only time sine is going to be valid. So sine theta equals p, a constant. That constant, for this whole situation to be workable or to be valid or to be defined, p must be essentially either 1 as an integer or a proper fraction between 1 and -1. Okay, so it's either the extremes or a proper fraction between them. Nice, nice, nice. Where does this knowledge comes from? Okay, let's just leave for now. Therefore, when we solve for theta, we're going to take the inverse of sine. Okay, so we take the inverse of sine of that value p, and we add 360 to it. Now this defines an angle in the first quadrant because we assume theta is some acute angle in the first quadrant. Okay, so that would be a general solution for that situation. And now what does that 360 represent? Remember, this means we will get again the same value only after 360 degrees have completed. All right, because we know that the period for a sine function is 360 degrees. All right, great. So let's just depict that fact on the Cartesian plane. We know that a sine function on the Cartesian plane would look something like this. That's the origin there, 0 degrees. So we know that the sine graph starts off like this. And we will simply say this is at 180 degrees. That is at 360 degrees. And we know that the peak is at 90 degrees. Of course, guys, it's not going to be nice, but this is just the idea. I want us to remember our grade 10 very well, because this is built from grade 10 knowledge. So this is going to be 270 degrees. Nice and easy. And what do we mean? We know that this would be the minimum value, and that would be the maximum value. Okay, so the minimum is going to be -1, the maximum is at 1. So this is why we say that constant p has to be the range of the sine function, because this is effectively the range of sine theta. Okay, so it's the range. Think about it. So this has to be within the range so that it can work. Now let's see. If we take a point, for example, here. Say we've got a point P. This point will only repeat. Maybe let's just sort this up a bit. So this sine function would still continue and complete yet another revolution again later on. Maybe it's nice to do 2 revolutions for now so that you can see what I'm trying to get to. Of course, we've completed our revolution. I'm going to break this up because we're not trying to do this part. I'm just increasing it for fun. Just for fun, so that you can appreciate the idea here. Now, can you see that point P is going to reach the same value at exactly 360 degrees later. So we can call that a reflection of P about some line, which we can choose what it is. But at this point, I'm not interested in that. So all I'm interested in is to display the fact that that point P will have the same y value as it is here, whatever that value is. Maybe let's call it, okay, let's not call anything. So can you see, if we take the x coordinate at that point P and subtract the x coordinate, P prime, and subtract the x coordinate at P, we will see that that would be an interval of 360 degrees. Hence we say this value will always repeat every 360 degrees. So that's what we mean by that period. So please understand, that's what we mean. That if we saw something in the first quadrant, we'll only see it again after 360 degrees. Or should we say at exactly 360 degrees later. And it will keep repeating like that because we can do multiple revolutions. That's why we call these general solutions. Okay, these are called general solutions in that they essentially cater for as many revolutions as we want. This dictated by the integer k. So k is an element of integers to then tell us how many revolutions we are looking at. Okay, so if we're looking at just one revolution, we're going to put 1. This could be either clockwise. In fact, if we put 1, that means we're doing anti-clockwise, one single revolution. If k is -1, it means we're going clockwise, one single revolution. So this is what we're doing right there. Okay, hope this is clear, guys. Please, this is not very difficult, but it's something to really think about carefully. Now let's look at number 2. Number 2, we are given some cosine of an angle theta. And this is supposed to give us some constant p. Again, p here is a constant. Remember that. P is a constant. All right, it's not a variable per se. It stands for a specific value. Okay, great. And now this would effectively be its range. So that would be the range of the cosine of theta or angle theta. Very important. Again, this is only valid when that constant is either 1 or less than 1 or equal to -1 or greater than -1, essentially suggesting that it's a proper fraction between those two extreme values if it is not one of those extreme values. All right, good. So if that's the case, we can then solve for the angle by taking the arc cos of that value p, and then we add 360 degrees times k, meaning k is an element of integers. Now k is simply as many revolutions as we want. Okay, so that's very nice. That's very nice. But again, think about it. There are some issues that we actually cater for here. Nice and easy. And of course, this is nothing but a general solution. But what is important is that we can say this is either plus or minus. So we don't have to worry about this whole situation where we set angle in the first quadrant and angle in the second quadrant, essentially, because we assume that p is a positive answer. Remember, whenever we formulate a mathematical expression or theory, we try to look at it in terms of the positive aspects. That's why we always try to adjust things so that when we talk about things in principle, we consider them positive, even though we will still be able to accommodate the negative aspects. So here sine is positive in the first quadrant. This is exactly what this means. And this means it will only repeat after 360 degrees, whatever that was. And the same situation here is saying 180 minus the arc sine, meaning this angle right here will only repeat its value after a period of 360 degrees, no matter how many revolutions we want to look at. Okay, so the same here. So this one is much shorter. Just say plus or minus the arc cos of p plus k times 360 degrees, where k is an element of integers. That's again a general solution on its own. Now let's look at this cos or cosine function on the Cartesian plane, because it's very nice to always consider this on the Cartesian plane so that we know what we are dealing with. So that would be 0 degrees at the origin, and we know the cosine function starts off at a maximum, grows and completes its cycle, and then let's take another cycle. All right, good. So this one, I'm actually doing it so that we can see what I was trying to say in the first instance, so that we can understand why these two are so similar. Now it hits the x-intercept at 90 degrees, and then it hits its minimum at 180. So this is at 180 degrees, and then it hits an x-intercept at 270 degrees, and it will hit its max at exactly 360 degrees. And we can see that this is a full cup of the cosine function. So this means it has completed its period or full revolution. This is yet a second revolution. Now, folks, what do we mean by this period issue? It means if we look at some point A here, this point A will only repeat itself at exactly 360 degrees later. So that would be the mirror image of A for the same y value. Okay, I hope this is very clear, guys. So if we take the x coordinate at A prime and subtract the x coordinate at A, we will see an interval of 360 degrees. So this means if we saw this y value here, we'll only see it at exactly 360 degrees later. Okay, so that's the understanding that we need to keep in mind. Okay, that's the understanding we need to keep in mind. All right, guys, so I hope this is very clear. Now let's have a look at some tan theta. Now that angle theta, it's a variable, we understand it, but P is a constant. Remember, P is always a constant here. So that's a constant. But now look at this. You'll appreciate that P is an element of real numbers this time. So there's no limit because the tan function is not limited vertically. So in terms of the range, there's no limit. But in terms of the domain, we may be, depending on what we want to do. So this is the range of a tan theta function. Remember that, it's the range, and there's no limit to the range. But on the domain, we know that we have asymptotes. So we have some, limited points that we don't get across, essentially. All right, and of course, this would be its general solution. But now, this situation says theta is going to be the inverse of tan of that constant P. Then we add 180 degrees. 180 degrees, why? Because the tan function completes its full period, or should we say its full revolution, if we think about it that way, at 180 degrees. So this means in the span of 360 degrees, it will have completed 2 revolutions, if we think of it as a revolution. But we can just easily say it's a full cycle. Let's just not call it a revolution. Okay, or a full period. Nice and easy. And k is an element of integers, meaning however many these periods are. Okay, let's have a look at it on the Cartesian plane. Now this is all from grade 10, guys. Please don't forget. Do not forget grade 10 stuff. It's dangerous to do so. No one is allowed to forget grade 10 stuff. Okay, so that's 0, the origin. We know that we will have an asymptote at 90. So this is something we need to know, standard stuff. And we will then complete a period at 180. And we continue. Okay, we will have another issue at 270 degrees if we're going for 360, so that we can do the things that we need. Okay, so we know that this situation here, halfway, which is 45 degrees, this is going to be 90 degrees, and then we're going to have 180, and then this is going to be 270 degrees, and we end up at 360 degrees. Okay, now let's see what happens to this function. Tan of 0 is 0, and then it does its own things. Okay, it's not quite nice. I'm not liking it. That's much better. So we can understand that the tan graph does this, and it will do this. Okay, that's what it's gonna do. So it gets there. So it doesn't really cross the asymptote, and of course it continues its own business like that. Okay, now this is going to still go on same way, and then let's leave it at that. let's leave it at that. That's where we stop. Okay, now there's some important areas like this one here. The tan of 45 is a special case, isn't it? It's a special angle. It always gives us the value 1, but that's not a maximum, but we know that tan of 45 is going to be exactly 1. Now we can call this point maybe B. When are we going to see this again? Exactly 45 degrees, 180 degrees later. At exactly 180 degrees later, so this should be our B prime. Now what would that be? For us to get to 180, so this should be essentially 225. 180 plus 45 is 225. Okay, and we can see that if we take that 225 and subtract 45, we get a period of 180, as we have stated that these two are exactly an interval of 180 degrees. So you can see that that's what we mean, that this one repeats the value at a particular angle at exactly 180 degrees later. Hence we say the period is 180 for this one. Alright guys, so I hope this is very clear and nobody misunderstands this, because it's dangerous to do so. Alright, now as much as there's a 1 there, there's a case when we have -1. I'm just going to force it here and say this is the case when we have -1. When do we see this -1? Okay, as you can see, 90, it's going to be intervals of 45, isn't it? So 90 plus 45 is going to be 135. So this is 135 right here. So it gives us -1. And when is it going to repeat again? At exactly 45 degrees later. Not 45, sorry. 180 degrees later. Okay. So 180 degrees later, 270 plus 45, that's gonna be 300 and stuff. Is it 315? I think so. Let's see. If you calculate, I am Manchi. Yes, Manchi. Masibone, 270. High. Plus 45 from Palagaga. Yes, 315, this one. So can you see? If you take, for example, let's call this point a different name. Say this is point D, for example. This would be D prime. And we can see if we take the x value at D prime and subtract the x value at D, we will have an interval of 180 degrees, meaning everything keeps repeating itself like that. Now here's how you see the full period on the tan function. If you follow this and you take that, that's a full period. Okay, so same story, you can look at it in terms of this one and say that would be yet another part and another part. That makes up a full period. Or just focus on this whole thing. Okay, let me answer the question. Alright guys, so this is essentially how we can think about this. So it's either this and that makes a full period, or from here all the way up, that's a period, because 270 minus 90 gives us 180. Okay, or we can think of that top part and then that bottom part, that makes a full period. Okay, so I hope this is super duper clear. What is this word again? Yeah, you can't eat no lemon squeeze, God. Anyway, so let's have a look, guys. Now here are some nice considerations as well. So this situation and that situation. Now, when we have sine of an angle equal to cos of that same angle, it means we can divide by cos such that we have sine over cos equal to 1. okay, as the cos's will cancel on this side. Okay, let's say they divide to 1, because they don't actually cancel, but they kind of, blend with the background like a chameleon. All right, so 1 is a chameleon of maths. Then this goes to tan theta, essentially using our identities. And this helps us to solve generally like that. And of course, any x values, by choosing our k values, we can actually find the exact angle that we need given a particular domain or constraint. Again, let's say we have a situation where the sine of theta is equal to the cos of beta, meaning the angles are not the same this time. The angles are different. Now, when the angles are different, we cannot divide by cos or sine here, because it doesn't satisfy our identity. So we can use cofunctions, because we know sine and cos are cofunctions. So if we choose sine to be the leader here, we can actually change the cos of beta to be the sine of 90 minus beta. Okay, and now this helps us to say, if this is the sine and this is the sine, therefore this angle is the same as the theta. Okay, because if the sine of a particular angle is equal to the sine of yet another angle, as much as the angle may look complex, actually the angle must be the same, because sine defines that value. Okay, so great. So that means we drop the trig ratio and we just equate this, and using the same general solution, this would be essentially an angle in the first quadrant in principle. As complex as it looks, once we say sine of this particular angle, this angle in principle is anyway, so that is 90 minus beta, and then we essentially do the general solution as we know how. And of course, for sine, we always consider 180 minus, because we assume this is an acute angle in the first quadrant. And now we need to find its equivalent in the second quadrant, because sine is positive in those two quadrants. And of course, we do the general solution as we know how. So please be in a position to spot this and be able to use it. Okay, now this we can take down and say, what if we choose to solve for beta instead? Then of course we use the same idea of corratios. We will choose to change the sine of theta into the cos of 90 minus theta, and then we solve for beta. And again, as we solve for beta, we just drop the we drop the causes, and therefore equate that angle. But for this one, we're going to always say plus or minus, like we do for cos. So I hope this is clear, guys. We're going to start working on some questions now, because this introduces nicely the trig functions. Because when we're doing trig equations, we're literally essentially needing to think about it in a function sense, so that our lives can be easier. So please know these things, guys, and master them. Okay, know these things and master them. You will find this worksheet in the description if you need it to download. Okay, and perhaps these solutions I'm also going to include together with this, all right, into one single document. Now remember, guys, our three-step approach. Remember, in maths, I don't care where you are and what level you are, when you are solving, you are literally playing around that three-step approach. Trust me, it's something very, very useful, and it helps you to not even crack your skull. It's more like learning log multiplication. When they say don't use a calculator, you're actually using a calculator, but without really touching a physical instrument. Okay, so this is more like it here. You just have something that actually tells you what to do and when to do it. Of course, you need to be the judger of what is best at a given point or for a given step. Okay, let's start with question 1. Okay, we're going to try and move quicker here because we already know what we are doing. Now, question 1 says we need to solve for theta if sine theta minus 1 is equal to cos 2 theta. So we're going to write here sine theta minus 1 equals cos 2 theta. Now we know that from our 3-step, we can see there are no like terms as yet. We know 1 is essentially an identity, but cos 2 theta is a more clearer one. So we can leave that, and if we have sine here, it means we need to represent this in terms of sine so that we can achieve a quadratic trinomial. So we almost always try for that, okay? So we're going to have sine theta minus 1 is equal to, this one is going to be 1 minus 2 sine squared theta. All right, so now we take everything to the one side. This implies that we're going to have 2 sine squared theta. We're going to write them in descending order of their powers. Sine theta. Then we have minus 1 is equal to 0. Okay. Right. Let's try to put things nicely. And then, now we have a trinomial. But now, can we factorize this trinomial? Maybe. Maybe not. You know. So this is what we have. Let me think. Oh, Lord, I forgot. This one, when it goes to the other side, we get a minus 2. Okay. I almost lost the battle here. Now this one, if you're not so sure, always check the discriminant. B squared minus 4ac is equal to, the coefficient of sine is 1 squared minus 4 into the coefficient there. Remember, b here is the coefficient of sine, which is an invisible 1. We don't write 1 sine theta. It's just invisible 1. And then a is the coefficient of sine squared. Remember, the variable is sine here. Okay, sine of an angle. So this is going to be a, which is 2. Okay, so this is a quadratic, guys. Please, you don't need it in terms of x to see that. And then c is going to be our minus 2, which is the constant. So let's see, is it a perfect square? So this is 1. Now this is 8 by 2, 16 plus 1, 17. So the discriminant is not a perfect square. So this means we cannot factorize. So when you're not sure, don't crack your skull. Just see if you can factorize or not. If you can't factorize, you know that we need to use the formula. I don't know why this thing, hey, one. So this means that sine theta, remember we're solving for sine theta, it's going to be minus b plus or minus the square root of b squared minus 4ac all divided by 2a. Sine theta is now minus into 1 plus or minus. We've got 1 squared minus 4 into 2 into minus 2 all divided by 2 into 2. Okay, so again, as I said, guys, follow the same pattern. So b is what we substitute there, and then a is what we substitute there, and then c is essentially what we substitute there. Of course, we already know that this is square root of 17, but it doesn't really matter anyway. So this implies that sine theta is equal to, now let's put it on the calculator. We've got 1 in minus into 1 plus the square root of 1 squared minus 4 into 2 into minus 2 divided by 2 into 2. All right, so my first answer. Now guys, here remember, this is not the final answer, so we write it as it appears. So this is minus 1 plus the square root of 17 over 4, or sine theta is going to be, this one is going to be, we can factor out the negative, it becomes minus 1 plus the square root of 17 all divided by 4. Okay, so the effect of factoring this is just to show that this is going to be the negative one, or the one that gives us the negative value. Now, what are we going to do? Remember, we are solving for theta, so this implies that theta is going to be the arc sine. By the way, let's first check which one of these are these both in the range. Let's see. So this fraction minus 1 plus square root 17 over 4, what is it? This is 0.78, so the first one is valid. Let's look at the second one. This one is minus 1.2. Can you see this is outside that range? Minus 1.2 is outside the range, so we reject this solution. So always check first if any solution is to be rejected before you waste time using it in the solution. So this is the arc sine of minus the arc sine of minus 1 plus root 17 over 4 plus k times 360 degrees, or theta is going to be the arc, we do it the way we do it, 180 degrees minus arc sine of, holy cross, minus 1 plus root 17 over 4 plus k, maybe let's move it a bit to the left, so k times 360 degrees, where k is an element of integers. Okay, so that is the story. So this is how we derive general solutions. You can use the reference angle method, it's still not a big deal. Actually, at this point we can just sort it out and say therefore theta will be, so let's do it. So we're going to say arc sine that minus 1 plus square root 17 all over 4. So that's exactly what we are doing here. So this is going to give us 51 to 2 decimal places 33 degrees plus k times 360 degrees, or theta is going to be equal to, now as you can see, the shift sign of that situation is nothing but exactly the same angle on the other side. So there we can take this one from 180, and then what we do is gonna be 128.67 degrees plus k times 360 degrees, where k is an element of integers. But remember, we were not given any domain, so this is the value for theta. So this is another way to ask for general solutions. So when you're told to solve and there's no domain given, you just simply do general solutions, so don't sweat. So you can see, guys, the quadratic formula still applies. Just to emphasize the fact that we're still doing algebra. Okay, let's get marks. Whenever we use identities, that's a mark, okay? essentially writing our quadratic in standard form. Well, maybe it matters because this time we are essentially applying it. So this is a potential mark, but the best mark is for substitutions here. And sometimes rejecting this solution may be looked at, and accepting that solution may be looked at, and then these two general solutions. So we have 1, 2, 3, 4, 5, 6. Usually this is okay. You will almost always be looking at 6 to 7 marks when asked to do this kind of a situation. At times they state it nicely that solve for the general solutions. Sometimes they don't, like here. You have to figure it out. If I don't have a domain that I'm given to find the exact x values, values of the angle theta, then I literally just do general solutions. Now let's talk about this. Now you can do the reference angle method, which is still the same thing, because with the reference angle method though, you will miss the other solutions, because the problem, you may not add these unless you are going to remember to do so, because you may be forced to just find this angle and that angle, because with the reference angle method, that's what you're gonna get. It's 128,67 and that. But are they the only solutions? Now without the domain given, they are not the only solutions. So choosing the two, those solutions are incomplete. You actually may lose those marks unless you're going to remember that after finding those reference angles, then you're going to add the period to it. And of course, K is just suggesting however many revolutions we want. When K is negative, we know that we're doing the negative angles, or at least the clockwise rotation. When this is positive, we're doing the anti-clockwise rotation. And when this is more than 1, then it means we're doing as many revolutions as the coefficient states. Okay, so that's essentially, guys, the story. And I think there's nothing much to say. Let's take another question to further our thought process here. Can I squeeze it here? Maybe. But I don't like to clutter things, but let's try. Okay, maybe let me leave the space so that if anyone wants to write some extra notes later on, that space can be available for that. Now question 2, we are solving for x if 3 cos 2x minus sine 2x minus 1 is equal to 0. So we have 3 cos 2x minus sine 2x minus 1 is equal to 0. Now we can see this is already a trinomial, so we need to try and make it look nice. But of course, this decomposes into sine and cos as a product. So we need to think about this one. What are we going to decompose it to? But now there's 3 things to consider here. Is cos 2x. We need to consider sine 2x as well as 1. Not the negative 1, but 1 alone. Now this one is a bit tricky. Again, we know that on our 3-step approach, we have identities there. So identities are going to force us down the path of saying this is 3 into. Now since this is going to decompose to both sine and cos, we might as well decompose this to both sine and cos. So this is going to be cos squared x minus sine squared x. Okay, minus this one decomposes to 2 sine x cos x minus into 1 itself is just sine squared x plus cos squared x using the square identity equal to 0. Okay, I cannot do anything about the drifting situation there. Even if I try to correct it, it's going to overwhelm me. All right, so now we just FOIL things out. So we get 3 cos squared x minus 3 sine squared x This is minus 2 sine x cos x minus sine squared x minus cos squared x. Lord, I didn't write the expression. Oh, by the way, the 1 disappeared. Alright, so this is what we have. Can you see? We're cruising nicely. Now we've got like terms. This and that are like terms. So we sort it out. So 3 cos squared x minus cos squared x is going to be 2 cos squared x. Okay? And then we have like terms again. 3 sine squared x. So minus 3 sine squared x minus sine squared x is going to be minus 4 sine squared x. And in fact, I would rather we push this away so that we can see our trinomial nicely. We want this middle term here. This is 2 sine x cos x. Okay? Now this is equal to 0. So now we have a trinomial, but 2 is still a highest common factor here. We divide by 2, we get cos squared x minus sine x cos x minus 2 sine squared x equal to 0. Okay, now we can try to factorize here. Usually we win, sometimes we don't. Okay, the reason I'm already going for it is because I have had a lesson with my students, so I know this one is going to work. Okay, and then we want this to give us minus 1, so this must be minus 2 sine x plus sine x. Right, and then what are we going to have? This implies that we will have, now we can try to define sine here. I think it's easier, or we can use cos. Maybe let's use cos, but let's not use cos. Let us not use cos, let's use sine, because once sine is on top, let's let sine be on top. So sine x is going to be equal to minus cos x, or 2 sine x, just think of it when we just transpose, this is going to be equal to cos x. Easy. Now, we know that we can divide by cos x on both sides, so I'm not going to even write that step. Sine x over cos x is going to be equal to minus 1, or here we are going to be forced to divide by 2 cos x. So this is going to end up looking like sine x over cos x is a half. Alright, okay, alright. Now we know that this is going to be 10x equals minus 1, or 10x is a half. Therefore, we know, okay, maybe let's not rush it. So trig equations are a bit naughty. So this is going to be the shift 10 of minus 1 plus k times 180 degrees, or x is going to be equal to the shift 10 of a half plus k times 180 degrees, where k is an element of integers. Now, this is what we do. As you can see, our notes on the left hand side are guiding us. For 10, we don't need to consider anything because the period is much shorter, so everything repeats much faster, so 180 is good enough. So we can make a conclusion. Therefore, x is going to be, now shift 10 of minus 1. This is going to be minus 45 degrees plus k, 180 degrees, or x is going to be the arctan of a half. Okay, I don't know, this one is not a special one. Arctan of 0,5 is 26. 5 7 degrees to 2 decimal places plus k times 180 degrees, where k is an element is an element of integers. Now we didn't have a domain, so we leave it as a general solution, because once we are told to solve and there's no restriction, we need to cater for all solutions. As I said, if this is missing, guys, if you're missing the period stuff, you are dead. But if you just write minus 45 and 26, those are part of the solutions. They're not complete. So I will ignore that part for a student who doesn't present the answer right. Now let's say this was the reference angle situation you wanted to do. Remember, minus 45, when k is 0, this kills the second term. Minus 45 is an angle in the fourth quadrant, so 10 is negative in the fourth quadrant. This would have been catered for by that. Well, this is as good as 360 minus 45. Guess what we get? We are going to get an interesting answer, which is 315. So minus 45 degrees is an equivalent of 315. So it doesn't matter what you do. This one, 10 is positive in the first quadrant. When k is 0, this is 26,57. That's an acute angle in the first quadrant. So this would be good. But again, 10 is positive in the third quadrant. When k is 1, that means after 180 degrees, we just simply say 180 plus 26. Guess what? That would give us the angle in the third quadrant where 10 is positive. So this is good. But the good thing is that as many revolutions as exist, we need to cater for those solutions. I hope this is clear, guys. Again, how many marks are we going to get? Remember, every time we use identities, 1 mark, 1 mark, 1 mark. So 3 marks nje. So kanje. Now foiling out is not a big deal, and whatever you are doing is not a big deal. What matters is the factorizations. Okay, good. And then from there, what matters is when we use identities here, this 10 and that 10, because these are essentially identities. So we get marks there. Can you see already? 1, 2, 3, 4, 5, 6. Now we can mark this one as the 1 mark. We never get more than 7 marks for general solutions, but we may choose to give because this stands in for 2 solutions, and also this one stands in for 2 solutions as well, because 180 minus this would be an angle in the second quadrant and an angle in the fourth quadrant. So maybe let's mark it as well. We cannot ignore it. So maybe 8 marks. Maybe I'm going for the kill because we used the same identity here, so maybe we can just mark this step once, because we're not marking the values here, we're literally marking the identities. But let's leave it, guys. It's not a big deal. All right, so I hope you understand. I hope you can follow. I hope this is as clear as the back of a goat. So I'm going to leave this space for anyone who wants to jot down some notes, because this is going to be on the description, guys. This is going to be on the description. I'm a bit hungry. Hey, I'm not resting these days, guys. There's a lot of preparations we are conducting here. So yeah, I'm not exactly relaxed. I don't really sleep that well, so I'm feeling a bit jittery. Anyway, let's look at this one. We're solving for alpha when this situation is the case. Again, we're not given any constraint or domain. So this means general solution. So I want you guys to get used to answering questions even when they are vaguely given. So it's not a must, okay? So let's see. This is cos 2 alpha plus 6 is equal to 4 sine squared alpha plus 5 cos alpha. Okay, so again, this is an equation. We just need to plan how we're going to do this. Now, as you can see, this is in terms of, this is cos 2 alpha, this is sine squared alpha, this is cos alpha. So cos alpha is never going to go away. Because of that cos alpha, we need to change everything into cos so that we can have a nice trinomial. So this implies, so this is going to be 2 cos squared alpha minus 1. Okay, in fact, we don't need the brackets. This is an identity. It decomposes like that. Plus 6 is equal to 4. Sine squared is basically 1 minus cos squared alpha plus 5 cos alpha. So a bit of inspection is useful here. Alright, so we have 2 cos squared alpha minus, in fact, we can just sort this out. These are like terms. Minus 1 plus 6 is just plus 5 equals, with FOIL, this is 4 minus 4 cos squared alpha plus 5 cos alpha. Now we bring everything to the right hand side. This is going to be plus, so we get 6 cos squared alpha. Then this one becomes minus, oops, I forgot to write this properly. So this is 5 cos alpha. So this is also going to be minus 5 cos alpha. And then we bring in the 4 to the other side, we get plus 1 is equal to 0. Okay, so this is good. Now we cannot do anything but try and factorize. When in doubt, check the discriminant by using the coefficients here. That's what's going to work. So we want 5. Both brackets are negative because the last term is negative. The last one is positive. The middle one is negative. So we need 3 cos alpha and 2 cos alpha. And then we're going to have minus 1, minus 1. Can you see? Minus 3 cos alpha plus 2 cos alpha will give us minus 5 cos alpha. So this is done. So this implies that cos alpha is a third. A third is a proper fraction within the range for cos. So this is good. We accept this. Or cos alpha is equal to a half. Again, a half is a proper fraction within the range. So this is all acceptable. From here, we're going to say this means alpha is equal to plus or minus the arc cos of a third plus k times 360 degrees, or alpha is going to be plus minus the arc cos of a half plus k 360 degrees, where k is an element of integers. Okay, so we make a conclusion that our alpha is, now let's see, what is arc cos of a third? 1/3. So this is 70, 53 to 2 decimal places plus k times 360 degrees, or alpha is going to be equal to, now arc cos of a half is going to be plus or minus 60 degrees from special angles. Okay, So k is an element of integers. Now we are done. Again, this was a question on general solutions. So we need to solve this, and trust me guys, master the general solutions, because you will solve anything, even when it comes to the graphs. The points of intersection are just easily done this way. Of course, we'll modify your way of doing things depending on the question, because sometimes it is just as good. Okay, now remember 70, the plus 70, I forgot to write here the plus minus. Now the plus component, when k is 0 here, killing the second term, this would be an angle in the first quadrant, and cos is positive there. But cos is positive when the angle is negative, because minus 70,53 is an angle in the fourth quadrant. So this plus or minus caters for every situation where cos is going to come out positive. Even when negative, it corrects itself, okay? It always does. So guys, this is nice. So how do we score marks here? Remember, we used an identity. Every time we do so, we get marks, okay? Now the rearrangement and stuff doesn't matter. The factorization does, okay? Maybe both these solutions, we can mark them, but they are individual solutions. They are both valid. Maybe let's just give it. Why not? And then give a mark for each one of those solutions. So this is again 1, 2, 3, 4, 5, 6, 7. So usually these are the marks that get scored for this kinds of questions. These kinds of questions demand as much. So guys, you should be comfortable by now. This thing should be nice and easy. You see, it should be nice and easy. All right, so let's go on to question 4. Again, I'm going to leave a space for anyone who wants to fit in some notes if you're studying along. But if you're not, then it's okay. So you can download this and use it. All right, 4, we have A. Now we need to prove that square root 2 sine of this complex angle or compound angle is equal to sine x plus cos x. So we need to prove this. So we need to say, okay, square root 2 sine of x plus 45 degrees is equal to sine x plus cos x. Okay, so basically we just need to prove that the left hand side is equal to the right hand side. Okay, so we can do this. This is more like an identity. Right. Okay, maybe let's do it like an equation, just to show you something special. In maths, we are allowed to divide by anything we want. So this time we're going to divide by square root 2. So we isolate sine x plus 45 degrees is equal to, this is going to be sine x over square root 2 plus cos x over square root 2. Okay. Now, this is going to imply, now we can see this situation here is nice like this, so there's no need to manipulate it. Is equal to, we factor this out, it's going to be 1 over square root 2 sine x. It's nicer when we do that. We factor out the root 2 there, because it's on the denominator, it's going to drag a 1 on top. So this is what we have, and we're like, hold on, this 1 over root 2 smells like our special angles when our situation is like this, where we have 45 degrees and 90 there. So this is 1 square root 2. So that's the special triangle that smells like what we see here. That smell is good. Is a smell of meat. Is a smell of meat. So this implies that sine of x plus 45 degrees is equal to, now remember, if we say this is a sine, we want to change this into the sine compound angle expansion. So this is going to be, now we're going to choose cos here. So this is going to be sine x, we make it lead, times, we know that cos of 45 is going to be adjacent of hypotenuse, which is 1 over root 2, which is the same thing. So we say this is cos 45 degrees from special angles, plus. Now we're going to let cos x lead the way. This one we're going to choose sine, so that we know that sine of 45 is opposite of hypotenuse. So this is as good as sine of 45 degrees. We're choosing sine strategically because we want to see if this side is going to be exactly the same side as that. This implies that, okay, maybe let's say, okay. This implies that sine of x plus 45 degrees is equal to, now this is the compound angle identity for sine when it is expanded. So we can contract sine of the first angle plus the second one. We can say therefore the left hand side is equal to the right hand side, because you can see it's the same thing. So the identity has been proven, so you can just prove it like an equation. This is more like solving both the left hand side and the right hand side equally. Okay, but the standard approach, guys, let's just show a bit more here. We would choose the left hand side because the right hand side is already simple. We say square root 2 times sine of x plus 45 degrees. This is going to be equal to square root 2 into, we expand here, this is going to be sine of the first angle, cos of the second angle, the sine remains, then it's going to be cos of the first angle, sine of the second angle. Nice and easy. Now, cos 45 from special angles is going to be 1 over square root 2. 1 over square root 2 times sine x plus sine 45 is going to be 1 over square root 2 times cos x. Okay, now when we distribute this dude, it's going to cancel these guys, which is going to be just sine x plus cos x. This is equal to the right hand side. This is the standard way of doing it. But now I just wanted to show you guys when we are doing equations, we just do it. As you can see, it's much longer when we did the equation. It's much shorter when we do the standard approach, whichever you choose, it works out, guys. It's not a big deal. So here we used the expansion, we get a mark. Then special angles here, we get a mark for each. The final answer was already volunteered, so not a big deal. So this one would be maybe 3 marks, roughly. And then here, when we divide, doesn't matter. We factor out, not really such a big deal. It's already given. We didn't do anything special, but changing these is what matters. All right. Okay, and then using our identities to reduce this, that's as good as that. So this would still be 3 marks. Okay, so this is good, guys. It's not too bad, is it? Not too bad. Okay, let's look at B. B says, hence or otherwise solve for x. Now we are given something else now. This is minus sine x minus cos x is 1 over square root 2. But now if we're told hence, It means what we were given above we need to use. But now it doesn't look quite right, so we need to do something first. This implies we factor out the negative. We get sine x plus cos x is equal to 1 over square root 2. Now we can multiply on both sides by minus 1. What do we get? We get sine x plus cos x is going to be minus 1 over square root 2. Great. Now we have it the way we know. But guess what? What did we get told? Sine x plus cos x is this left hand side. So we replace it with that. So this implies that basically square root 2 sine of x plus 45 degrees is minus 1 over square root 2. Okay, so this is good. Now, this is already proving to us that now we can solve for that compound angle. Ooh, we're gonna run out of space. I hate it. I hate it. I hate it. I doesn't like it. I doesn't like it. Okay, guys, the first thing here, we're going to need to divide by square root 2 on both sides. So this means sine x plus 45 degrees is going to be equal to, remember when you divide by this root is going to multiply in the denominator, so this is minus 1 over 2. Okay, all right, okay. Now what we have to do is to say, maybe let me try to make this into one line. This is 1 over 2. Okay, so this implies that x plus 45 degrees is going to be the arc sine of minus 0,5 plus k times 360 degrees, or x plus 45 degrees I don't know what happened here. This is x or x plus 45 degrees is going to be 180 degrees minus the arc sine of minus 0.5 plus k times 360 degrees, where k is an element of integers. Nice and sweet. So this implies that x plus 45 degrees is equal to, now we know that sine of minus 0,5 is going to be minus 30 degrees plus k times 360 degrees, or x plus 45 degrees is going to be, now remember this is going to be 180 minus 30, so this one is going to be 180 plus 30, which is 210 degrees, where k is an element of integers. Right? Nice and easy. So we can make our conclusion that therefore x is, transpose here, it's going to be minus 30 minus 45 is going to be minus 70 degrees. Or x is going to be, transpose the 45, 210 minus 45. Come on, it's going to be 210 minus 45 is going to be 180. It go. If it's 165. 210 minus 45. Organ is 45 here. It's going to be 165. Plus k times 360 degrees, where k is an element of integers. Now we have sorted that, because we're not given the domain, so we literally do all the things that must be done. Okay, I'm hoping that, guys, you can follow. You can see exactly what we are doing. Can you see sine is negative where? In the fourth quadrant. Remember, minus 30, it's an acute angle in the fourth quadrant. This is an equivalent of 330 degrees, right? Right. So if you're using the reference angle method, you'll get 330 here instead of 130. It's one and the same thing. Then here, it's in the second quadrant. As you can see, you would have done that nicely. And then, of course, we need to adjust because that was a compound angle. So we need to solve for x, not for x plus 45. Okay, how do we score marks here, guys? Easy stuff. Whenever we factorize, literally, we get marks. Then we uncover what we want and then the correct substitutions here. Is it there? Yes. The correct substitutions, in fact, not necessarily there, but here. And then, what is the story? Dividing here is not a big deal. Each one of these general solutions now. 1, 2. So this would be worth 4 marks. As you can see, there wasn't a lot that we had to do, but getting it right is what matters. Okay, so that's it, guys. Hope this is clear and that you're gonna master this thing. Okay, I hope you're going to master this thing. It is otherwise very interesting. It is very interesting. All right. Okay. All right. Now, don't be fooled by this angle right here. Some people may look at it and be like, but hold on, this is an angle in the second quadrant. But remember, when we're saying this is negative, it means k is not going to be 0. We don't kill the second term, but we put a minus 1 here. So minus 360, as you can see, 165 minus 360 is going to give us minus 195. But you see, where is 195? It's in the third quadrant. So that still places that angle there. So don't be fooled by the quality of the answers. If you understand what's going on, you will get the right message across. All right, let's do our last. I'm going to do this one as the last. Okay. This one is more of a higher grade type of a question. It's usually very tricky and taxing. This one, guys, I'm going to leave for you to do as homework. So we will mark it tonight. So this is homework. We'll be marking it tonight before we carry on, because tonight we are going to deal with trig functions on the Cartesian plane. So do you remember the page that I gave you guys, which has lots of paper 2 material? We're going to be looking at that paper. I'm going to just select some questions there on trig functions so that we can have enough exercise. I know you may have practiced them. It's not a big deal, but we're going to look at them nicely so that you can understand how to do those things. And I'm sure at the end of these lessons, you will be in that good position. Because what matters is to be in the good position. Okay, so let's do the last one so that I can let you guys be free for now. Then the last one is for you guys to practice, because it's going to be the basis of what we will do tonight. Okay, so I want you guys to try it out so that I don't spoon feed you too much. Okay guys, hey, kuhleketana ukutyeba kubonakalisa uba wondlekile, so ungakulinge nje undihlanyise ufuna ukusilima la. Hey, ungasilimi. Dala ndandifuna uba sisidudla, ndifune ndaze ndancama, ndisafuna nangoku uba sisidudla, but hey, andikwazi guys, kunini nditya. Khona wayithi mhla ndazisebenzela ndizawuba sisidudla, kodwa ngoku andisiso tu. Andize ndibe siso tu. So into enjalo, ndilibele ukubona someone, but I'm gonna go phansi ndalibala. Funa ndihambe ndimkroba phaa esibhedlela. Anyway, So guys, take a deep breath. We have come this far. Now the question says determine the minimum and the maximum value of this function f when it's like this, and you're like, what? So let's deal with it. So f of x is 1 divided by 3 sine squared x plus 4 cos squared x. Okay, so this looks complex. Now remember guys, in the function section or in the graph section, trig graph section, you may be given a particular function and you will see a sketch on the graph, and then you'll be told to use the graph to solve the following, and be like, what the hell? This doesn't even look like it. It simply means, look, 1 says the minimum value of 1 is 1. The maximum value of 1 is 1. So we cannot do anything about a constant. So this means that the challenge is here on the denominator. So the challenge is there. So we need to sort the denominator so that we can read it on the graph. If we are given a graph, then it means we need to simplify this into one of the functions, if not both of the functions, and then be able to read. But usually this would simplify into just a single function. That would be on the graph, and then we can use whatever we have on the graph to then solve further. So our task is to simplify the denominator. But now, while we are in that mood, let's just review some thought, because we need to understand what we're going to do. We know that, okay, if we've got 1 over 2, and we've got 1 over 4, and we've got 1 over 8, what is the answer for the first one? This is 0,5. The answer for the second one is 0,25. The answer for the third one is 0,125. Okay, good. But now notice something. As the denominator increases, the value becomes the smallest. So meaning we want the denominator to be the greatest for this situation so that we can get the minimum value. Right? Right. And in the same light, we can see that when we have the smallest denominator for the same numerator, we get the greatest ratio there. And so that means we need to consider both the maximum and minimum. So for us to say minimum value of this entire function, it means the denominator must be the minimum for this to be a maximum. But for this to be a minimum, it means the denominator must be the maximum. Okay, so remember, these are things to note before you solve anything. So you look at what you are given and you think about it. Once I solve this into a single trigonometric function, because this is how we solve this, we need to reduce this into a single trigonometric function. And remember, we never have squares. We never draw a function of any trigonometric expression when squared in our level. I don't know other levels, okay? Anyway, guys, so let's just simplify our f of x. So this implies that f of x is 1. Oops. 1 over, now we can change cos to sine, or we can change sine to cos. It honestly does not matter. Whichever you can think about is going to be good. All right? It's going to be good. So my mind tells me to perhaps change this into sine. So let's change it to sine. So this is going to be 3 sine squared x plus 4. Now cos squared is going to be 1 minus sine squared x, using our identities. This implies that our f of x is 1 over 3 sine squared x plus 4 minus 4 sine squared x. All right, so my battery is dying. F of x is going to be equal to 1 divided by, now we've got like terms, minus 3 sine squared x plus 3 sine squared x minus 4 sine squared x. This is going to be minus sine squared x plus 4. Okay, maybe this is too long now. All right, so we are going. So simplify, guys, simplify. The job is on the denominator. But now we can see that we cannot have a situation where the sine is squared. But now if we've got sine squared, can we change this into something else? Yes, if we think of cos 2x, this can be expanded as 1 minus 2 sine squared x. Now if we isolate sine squared x, what is going to happen? We transpose it to that side, and then we transpose this to that side. So we will have 2 sine squared x is equal to 1 minus cos 2x. Okay, then if we divide by 2, we know that sine squared x is basically 1 minus cos 2x all divided by 2. So this means we can do this and say this is as good as 1 minus cos 2x all over 2. All right, plus 4. Nice and easy. So again, this one is tricky in that the identity doesn't come out nicely. You have to make something the subject. So this is very important. Those identities, you can make anything the subject of the formula. So don't forget it. 1 is also part of that situation when needed to look like that, because we cannot draw a function for anything squared, okay? Is equal to 1 divided by, now we can essentially, well, first we can break this into a half and cos 2x over 2. Then we distribute the negative, so this becomes minus 1 over 2 plus cos 2x over 2. Maybe let's not write it that way. I don't like to write it that way. This is going to be plus a half cos 2x, yes, plus 4. Now we are getting somewhere. We can say therefore, okay, maybe let's not say therefore. Let's just continue implying. Yeah, this one is crazy, guys. It's a showstopper. All right, so we can see that this is as good as the half of cos 2x. Now 4 minus a half is going to be 3,5, which is nothing but 7 over 2. Nice and easy. So now this is a function. Yay, when this is a function which is halved but vertically shifted, 7 over 2 units. Now we know that the coefficient here, the absolute value of the coefficient, gives us the amplitude. And when we take the absolute value of the amplitude, we get the maximum. And of course, that maximum is going to take into consideration the vertical shift. All right? All right. Now we can solve using this thing. So we can say, therefore, the minimum value first. Minimum value of f is going to be equal to 1 divided by, now remember the minimum is always going to be the negative absolute value of the amplitude. So minimum is always the negative absolute value, whereas the maximum is always the absolute value of the amplitude. So this one is going to be minus a half, but we consider the vertical shift, minus 7 over 2. Okay, that's what we get. So let's get that one. So we can just do it on the calculator to avoid unnecessary strain. Minus a half plus 7/2. So I'm getting a third. Alright, so that's the minimum value. And therefore the maximum of f is going to be equal to 1 over, this time we are going to take, remember what did we say? And Gogil, I lied guys, I lied. No. Remember, for this to be a minimum, what did we say from our notes? For this to be a minimum, this must be a maximum. So we're taking the absolute value of the amplitude. So that's the case. So let's sort this out. Okay, so make sure you don't make a mistake here. So this one is a quarter. So that would be the minimum value. Now, we know that when this is maximum, it means the denominator must be minimum. So we're going to take the negative absolute value of the amplitude and consider our vertical shift. Okay. So this is the one that gives us a third. And we know that a third is bigger than a quarter. So this makes sense, because what made me even think about it was that the maximum value is going to be smaller than the minimum value, and that's not true. The maximum value must always be bigger than the minimum value. All right, okay, all right. So that is the story, guys. So can you see, once you know what to do, you just sort it out. But when you don't know what to do, you'll be dead. Now remember, this would mean if ever a graph was given or a function already, it would be something like this. But the examiners may decide to show it up like that, so that you have all this simplification to do to get here. Now on the graph, this would not even be a necessity to do this addition and stuff, since this was already a hypothetical function of some sort that wasn't drawn already. We had to use our knowledge. But if we had this already on the Cartesian plane, we'll just read the minimum value here, and we don't even need this. We'll just read it and put it there. And then we'll also read here the maximum value and put it there, and then calculate and get our answers. Okay, so this one was a nice one. So it's one of those tricky questions that usually are at the bottom of that function section. Sometimes it may be 4 marks, 5 marks, depending on the complexity. Here I made it a bit challenging by giving both the minimum and maximum value, but usually in there you'll be asked either one of the two, but not both. Okay, now let's mark this thing. So whenever we use identities, guys, remember simplification is simplification. And then whenever we use identities here, as we did, as strange as it looks, you don't need to show all of this, but you can put it there. It's good. And of course, now the trick with this one is, for the minimum value, it means we must make this one a maximum. So for that denominator as a whole, you get a mark. And for the answer, okay? Good. And then here, again, for this denominator, the way it looks, and the final answer. So this would be 1, 2, 3, 4, 5, 6. Okay, let's make it nice and 7, because this function needs to come out. So we can say this could be for 7 marks. Yes, yes, and yes. Alright guys, so let me live and love you here. Please practice these questions. Let me tell you one thing, guys, don't ignore your textbooks. Most of your textbooks are written using past exam question papers, okay? Because they want to avoid taking examples from another textbook. That would be plagiarism. And they don't want to write, because sometimes the books that they can choose are old. You can't even find the publisher. Maybe it closed down a long time ago. I've been trying to find a book here that I used in grade 10, 11, and 12 for physics, which was called Physical Science in Action. I cannot find the grade 11 and 12. And on these online shops, I only see it on loot.com or loot.com, but it's out of stock. So if you guys know any way I can get these books, please let me know. I know they are there in the school that I went to, Mkumbulo Comprehensive. I know there's these old libraries where they dump a lot of old books. I want to go there and check it out or find out. I would rather pay for them. Yeah, I like those books because there are certain things I have forgotten that I want to add, so that as I teach you guys, I teach you the right things. Because I cannot just use my thinking only and my memory only. Sometimes it doesn't serve me so well, so I end up losing the plot. Okay guys, hope you enjoyed the video, and do the last one as your homework. We're gonna meet tonight at 7 and sort it out, okay? And then get to the functions, because that becomes, our transition into trig equations or trig functions. I've already done some videos, guys, to go and preview, so that when we start working on some other issues or some different examples, it becomes much easier. The intention is not to have you watch me work. The intention is to inspire you to work on your own and to be able to see things beyond just what is obvious. As you can see, there are some things that you need to think about as you solve a question. Don't think you're going to be ready for every question. They're not going to repeat. Remember that. May June exams is going to be a completely new exam. But some questions are just similar, if not maybe exactly like these ones you've seen, but they will modify them just right to make them different, okay? But the concepts, the ideas are all the same. So you're playing around vertical shifts, horizontal shifts. We don't do inverses at grade 12 level, but we know that the inverse of a sine graph is actually minus the cosine. But again, leave that for later. There are very complex ways of actually proving that. The proofs are very strange, but you will understand them. But you will get to it when you do calculus higher than metric, okay? It's just too labor intensive. Anyway, guys, I hope you enjoyed the video. Leave a like, please, guys. Don't drop me. Don't drop me. Nina nendropa nina. Like is cheap, guys. It's free. When you see the video, why don't you just hit that like? Even if you don't like it, just like it, man. You're not doing it for me. You're just doing it for others. If you think the video is worth checking by others, just like it. Trust me. The algorithm will push my video up and recommend it for others to see. The idea is for all others to learn. Don't be a gatekeeper. Don't get information and then hold it because you don't want your classmates to match you. Be fair. God is also going to be fair with you. You will see things even better, because the one who shares and gives others a chance is the one who's going to be at an advantaged position. Trust me. Don't even think about it. Don't be mean. Okay? Don't have envy in you. Please, when you get something, share it with others. Of course, carefully so. But certain things are not to be shared, but this one is definitely to be shared. Alright, guys. I will see you again tonight. Have a good night. Please revise.